Let's go. So module 3, kinetics and equilibria for the 2023 Cape Cascade 1. Alright, lovely. So student placed a known quantity of frozen, I don't know what those numbers are, but I'm assuming it's N2O4 in a sealed tube and allowed it to warm up to room temperature. As the vessel was warming, a brown gas appeared, which indicated that the frozen N2O4 had vaporized to form a gas and then decomposed to form NO2 gas, according to the reaction below. The student allowed the reaction to proceed further until equilibrium was reached. Firstly, explain the term dynamic equilibrium. Go ahead.
Sir, so a dynamic equilibrium is the equilibrium that is in movement.
Right? It's in movement, but give me a more solid answer. What are the characteristics of a system in dynamic equilibrium?
The backward reaction is equal to the forward reaction.
Right. So a dynamic equilibrium is really a state in which the reactions themselves here, right, are reversible. The reaction is reversible, right, and the forward reaction is balanced out with the rate of the backwards reaction, right, and the concentrations of the reactants and the products remain the same. So, state in which reversible reactions have their forward and reverse rates balanced, right? While their concentration of reactants and products are the same. Or remain not the same, remains constant, by the way. So remains constant. So the amount of things in the system remain constant, but there's a constant production of reactants, right? And a constant production of products, right? And those things have a balanced rate. There's a reason why I don't use equal, but generally it's balanced equal, sure. Right? We can use that terminology. Okay? State what is observed when dynamic equilibrium is reached in the reaction above. What is observed?
I'm not sure, but would you have like a brown color?
Describe the tinge. I'm so sorry. Describe the tinge of brown. Would it be a dark brown, a slight brown, a little slight
Maybe
shade
a
of
light brown.
a light
Light brown,
brown?
like, yes.
Lovely. Okay. Would it change or would it remain constant, that light brown?
It would remain constant.
Alright. Say Le Chatelet's principle for me, please. Somebody else.
This principle states that when there's a change in a factor in a reaction, basically, then the reaction will what? It
No,
will try to oppose the change.
sure, lovely. But the thing is, no, but no, you know it, you know. You know it. I want to hear somebody else. Alright? So, the person who is raising their hand, go ahead.
Yes, sir. So it states that when stress is added to a equilibrium system, sir, the equilibrium, the system, the equilibrium shifts to counteract the change.
Alright. So, let's counteract the effects of the change. Alright? Fine. So, two persons gave two valid answers. Alright, so let's just this principle goes. So when one of the variables, right, that that are within a system in equilibrium changes, right, when variable changes, it could increase or decrease or whatever, right, the system will shift the position of its equilibrium to counteract the effect of that change. Lovely. Write the expression Kp for the reaction above. What is the reaction, K? What's the is the equation for Kp?
I think it's products over reactants.
All K's are products of
Cons-
reactants.
Concentration.
But it's still wrong though. Something-
NO2 in brackets raised to the second power,
no.
and then N2. What?
What?
No. I'm going to cry.
Huh?
We're talking
Sir,
about
that's right.
gases. They're not concentration. It's
Oh,
the partial
the pressure partial pressure.
Lovely.
Wait, so it would be P raised to the second power, then NO2, right?
So in this case,
On
yes.
the top.
Well, I forgot about them.
Yeah, so it's really that. So we're gonna have what? We're going to have NO2, the pressure. So we use regular brackets and we have the P, right? Divided by the pressure. N2O4, right?
Sir, aren't you supposed to raise the P at the top to the second power?
Yeah, we're gonna raise the partial pressure to the stoichiometric coefficient. Right. And that's Kp.
Oh, okay.
I think somebody has a question, go ahead.
Sir, so what is partial pressure?
Okay. So the partial pressure, right, speaks to this is in module 2, second topic, module 2. So the partial pressure of a gas okay, hold on. You know what pressure is, right?
Yes, sir. Yes, sir.
So if a gas is in a room or in a container, the pressure is the force exerted on the bombardment on the wall of that container, right?
Yes, sir.
Okay. So suppose it's air we're talking about. So air is exerting a pressure on that wall of that container, right? That's air. But air constitutes multiple gases. So the total pressure of the system is the overall pressure of air, right, in the system, right? But that total pressure is the sum of all the other minute pressures. So let's say that if there's a mixture of nitrogen and oxygen in a system, right? The total pressure is the overall pressure of the nitrogen and the oxygen, but the partial pressure speaks to the pressure exerted by only one component. So if you have nitrogen and oxygen in a system, you have the partial pressure of nitrogen. That means that the pressure that only nitrogen molecules exert, and if the partial pressure of oxygen, which is the pressure that only oxygen molecules exert, and when you add them together, right, you get the overall pressure of the system. That makes sense?
Yes, sir. It pretty much makes sense.
So what we describe that as is a Dalton's law of partial pressure. That is Dalton's law. All right. So that is that. All right. Great. So that's the Kp expression. Notice I'm not writing, but I am recording the information that I'm saying and that we're doing. All right. So let's have a shift over here. In the space provided below, draw a graph to show the concentrations of N2O4 and NO2, right, are expected to change as the reaction proceeds towards equilibrium. We know what graph we're looking at, right? Because I know the graph. Do you know the graph? I know.
Sir, equilibrium graph.
What
Sir,
equilibrium
but
graph mean?
it depends on if the reaction is a forward or backward reaction, I think.
It
No.
does. I
remember.
mean, technically it can.
Wait,
But what we're looking at, let's look at our scenario. Hold on. Look at our scenario and see whether or not it's backward or forward. Alright? So our scenario is saying that the thing is sealed, right? So we're starting with N2O, and what's happening is that as the N2O4 is thawing, right? the gas, as the gas is vaporizing, it decomposes it into NO2. So we're looking at the fact that we have N2O4 first, and we start getting NO2. That is what we're looking at, the forward reaction. So how would the graph look? So we're going to take a pencil and a ruler.
Okay, so
Go ahead.
I think it would look like I think that the N2O4 would be going down, and then the other one would be going up, and they would cross each other.
Lovely. Right? So this would be the N2O4, and this would be the NO2. And when the lines start to go directly in parallel with the x-axis, that means that the concentrations are the same, and that dictates whether or not our system is in equilibrium. Lovely. Moving on. We're moving on now, yes? Or are there any questions?
Yes,
Okay.
Alright, moving on. Let's go. Account for the shape of the... What do you mean account for the shape of the graph drawn? Okay, let's go. Account for the shape of the graph drawn. So with the graph, what's happening? So with this line here with the NO2, well, let's not talk about NO2.
So initially there were no products in the reaction.
There was
So
nothing
in
of
order
this.
for
There was none
Yeah,
of this.
yeah. So in order for there to be products in the reaction, the reactant N2O4 would have to decrease
Decompose.
so that the concentration of the product NO2 would
Mhm.
increase.
Mhm.
So that's why it looks like that. So that's why N2O4 is decreasing, and NO2 is increasing because N2O4 decrease so that we can have NO2 in the reaction, if that makes sense.
It makes sense. I think we all can agree that that makes sense. So N2O4 starts at an initial concentration, right? And as time goes on, its decomposition allows for the production of NO2, right? And
Yeah.
NO2 concentration continues to increase while N2O4 concentration continues to decrease until the reaction reaches equilibrium, which the rate of production of NO2 and the rate of production of N2O4 balances out and are equal. So that is shown by each curve reaching a plateau, right? Each curve reaching a plateau shows that they become, in the system of equilibrium, they become, they establish an equilibrium, alright? So hopefully you guys understand what the graph looks, because that's the question it's asking, right? The graph is basically saying, so you draw a graph, so like, do you understand what you draw say? That's what the question is asking, right? State what is observed when the sealed tube is cooled to 0 degrees Celsius. Outline the reasons for the reason. What is observed?
Sir, I'm not sure, but I think when it is cooled to 0, then that means it is an endothermic reaction. So therefore, the position of the reaction would shift to the right in order to increase the temperature.
Hold on. Okay, hold on. So what this mean? This positive value here, what that mean?
It's an endothermic,
Lovely.
right?
And as this is endothermic, yes? Endothermic mean cold. Lovely. Right? So what we're doing, we're decreasing the temperature. And as I said, if there's an endothermic reaction and you're decreasing the temperature, right? We're going to move to counteract that change, and that means that we're going to move to counteract that change in the exothermic direction, right?
Yes, sir.
Okay, hopefully everybody getting it. So if the
No.
forward,
So, sir, can you go? Sorry, can you start over,
okay.
please?
So first we have to look at our enthalpy change. Our enthalpy change here is positive, yes? So that means it's endothermic. And that means that the forward reaction is endothermic, right?
Yeah.
And when we speak about temperature, when temperature is decreased, we favor the exothermic. Hey, hold on. Let me think about this. When temperature is increased, right? Increased, we favor the endothermic. And if temperature is decreased, we prefer the exothermic, right? So what this is saying, right? The reaction is cold, right? So let's say it's endothermic, it's gonna be cold, right? So what's gonna happen now? If we keep on decreasing the temperature, making the system get colder and colder and colder, the Chatelier's principle says that when you make a change, we're going to move the equilibrium to counteract that change. So we're going to now be moving in the opposite direction, the exothermic direction, to counteract that decrease in temperature. Make sense? So if the forward reaction is endothermic, the reverse is exothermic. Gonna be negative. So if you picture it like this, right? If you're standing by a fire, right? The fire, let's say the place is cold, right? And you're standing by a fire. If you stand too close to the fire, right? If you keep on increasing your if you keep on increasing the heat, right, you're going to want to step back from the fire because you're getting too hot. That's what the Chatelier's principle is doing, right? So if it's an exothermic reaction and we start increasing the temperature, it's going to say, whoa there, we're not going to continue to create heat energy. We're going to step back and actually cool off, right? But in this case, it's cold. So imagine you're out there in the cold, right? You won't continue going towards the cold. You're gonna go towards the fire. So you're gonna. What's happening is that the Chatelier's principle is gonna increase the heat. It's gonna go towards the exothermic direction. So with temperature, when temperature is increased, the equilibrium moves in the direction of the endothermic reaction, and when temperature is decreased, we move in the direction of the exothermic reaction. That is what we're talking about. Does that make sense?
I still don't understand.
Oh my. Okay, what is it that doesn't really make sense?
How does this account for the temperature being 0? Because it's an endothermic, that's why.
Oh no.
I
Okay,
don't
okay,
understand.
hold on. Right? So let's read the scenario. Let's see if we can get some more understanding from the scenario. Oh, there's no understanding, never mind. Okay, so it was frozen, right? And we start thawing it, right? We start thawing it, right? So we start heating up the vessel, right? So look at this. The student, it was sealed, and what we do, we allow the person to warm it to room temperature. So the temperature now is in the range of room temperature, right? You see it from the question, right?
Yeah.
Okay. Now, the Chatelier's principle states, the Chatelier's principle with respect to temperature, right, states that if you decrease the temperature, we must move in the exothermic reaction, right? The exothermic direction, right? Yeah.
Yes, sir.
That is what it does. With decreasing the temperature, we wanna increase the heat, so we're gonna be exothermic. If we're increasing the temperature, we wanna actually get it down. We wanna decrease it, so we're gonna move endothermic. All we're doing is counteracting the change. We're doing the opposite, right? It's a very rebellious thing. So if we're gonna be decreasing the temperature too much, we want to increase the heat. We want to be exothermic. Right? So it's around the room temperature now, right? The question itself now begs the question, right? Well, we know begs the question, right? Let's see here. State what is observed when the seal tube is cooled to 0 degrees. We're decreasing the temperature. So what that simply tells us now is that when we look at the entire thing, let's go back up and we'll look at the entire thing now. Right? When it is cooled, right, what will happen? We see that the forward reaction is endothermic, and we say when we cool the temperature, we decrease the temperature, right, we're going to be moving the exothermic. So if the forward reaction is endothermic, that means that the equilibrium will shift to the right, to the left. You get that? We'll shift to the opposite. That makes sense?
Yes, sir.
Okay, so that is
Yes,
what's
sir.
happening, right? Now we're asked to tell what is observed. Can anybody tell us what is observed?
Oh, the color would change to colorless.
Lovely.
Wait,
So
no,
from
it would
brown
change to brown. Sorry. Wait, colorless?
colorless.
Wait, it's shifting. It's shifting to the exothermic side, basically.
Yes.
So it would change. It would change to brown.
Which one of the gases are brown? It is the NO2 which is brown. And if we're shifting away from the NO2, we will become colorless.
Wait, sir, I'm confused now because
Okay.
we are saying that it is an endothermic reaction, right? So basically, we're decreasing the temperature. So when the temperature is being decreased, it is shifting more to the endothermic side.
To the exothermic
So what we're trying
side.
to do is like we're decreasing.
If we decrease the temperature, we favor the exothermic.
Okay. Oh, so it's the temperature of the system.
The system, yes.
Just the system. Okay.
Yes. So since we're decreasing the temperature, we're gonna have a shift over into this. Oh my gosh, what am I doing on the screen? We're gonna have a shift in this direction, as you can see here, and we're shifting from brown to colorless. So what is observed in the system when we decrease it to 0 degrees Celsius? The color dissipates. The brown color dissipates. Right? Or the brown color disappears, or whatever you want to call it. Alright? That's 2 marks there. The first mark is for you to know that it shifts to the left, and the second mark is for you to state what happens. State the difference in behavior between a strong acid and a weak acid according to Bronsted-Lowry theory. Can somebody go ahead with that? What's the difference?
A strong acid.
Oh, sorry,
A
strong
strong
acid and
acid
strong base.
donates all of it.
Sorry, strong acid and strong
Strong
base.
acid donates all of its H plus ions in solution, while strong base accepts all the H plus ions in solution.
Lovely. Alright. That's fine. Or we could also say that strong acid decreases the pH by a lot. We increase proton concentration by a lot, while a strong base increases hydroxide ion concentration, which will increase the pH. Right? Could speak about stuff like that as well.
Okay.
Right? So it could be the consumption as well and the donation as well. Alright? Differences between them. That should be fine. It's a fine topic. Write the reaction for the dissociation of ethanoic acid. This is a repeat question. Repeat.
You would produce the ethanoate ion and the proton.
Most definite. Well, yes. Remember your double arrows. If you don't put your double arrows, I will not give you the mark. That's a personal thing. If it wasn't me, which mark you get? No mark. So let's look at this now. CH3, and that's why I want to finish my education degree thingy. Probably also at the diploma. Alright, so that's what we'll have here, and we're gonna have equals. Yes. Alright, 1 mark. 3 marks? No, 3 marks. I don't know why. Well, 3 marks. Table 2 now, using the variable x to generate expressions for the equilibrium concentrations of reactant components for 0.3 0.30 molar solution of our ethanoic acid, right? So let's look at that. I have to complete it blue by doing that. So what's we're gonna do now? Ice tables, right? So let's go. Wow.
So we're going to have a negative x for the change for the
Mm-hmm. All right.
so and for the hydrogen. Yes, sir. Yes, sir.
Mm-hmm.
That's basically it.
All right. That's not basically it. What equilibrium?
So well, they basically have a rewrite that.
You don't want the acid dissociation constant?
Sir,
In the acid dissociation constant?
sir, 0.30 minus x.
For the equilibrium?
Yes, sir.
Okay, let's see what you're doing. Go ahead.
And 0 plus x
I want to hear more. Go ahead. And you have 0 plus x over here as well.
and 0 plus x.
Alright. But like, no, we have to know the equilibrium concentrations. Now we'd like to know that. Somebody raise their hand, right? Go ahead.
Yeah, sir, it not gonna be could change minus 2x
Minus 2x.
instead of 0.3 minus x, yeah, minus 2x.
Minus 2x. Do we agree that it's going to be minus 2x?
How do you come by the 2?
That's what I want to figure out.
Because you remember you get two products.
Two
You get
products.
two products, you get H plus and you get the CH3CO minus ion. And those two, you get the plus X. And they taken away from the ethanol. So there's not how you gonna get a minus 2x.
But have a look at this. Right? If we look at dissociation reaction, right? That we wrote up here. Right? Oh my gosh, why is it? It's not going where I want it to go. My apologies. Alright, here. Alright? If we look at this here, right? It's one of these are going to be producing two of these. Why didn't I write a plus sign here? So one of these are going to be creating two of these here, right? So I'm not too sure. Okay, I think the 2x may be a valid assumption, right? But I'm not really sure where the 2x will come from.
Well, honestly, I want to see how y'all gonna work it because we don't work it like this.
Okay. I mean, the 2x has a valid assumption though. It's valid. I'm not saying that it's wrong. I've never said something's wrong. But it's valid. But I want to see how this goes. I'm waiting for somebody to go ahead. Nobody has any idea how to do this question?
Wait,
So
sorry,
we're
what's the
supposed.
question? What's happening?
What's this question? What's it about? What are we supposed to do? Are we able to do this?
Sir, are you
Yeah.
showing something else?
No.
So I think it has to do with the fact that the reason why the 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 product is the same concentration is because that it it oh boy, sorry, never mind.
Oh my.
I know how to explain it, but I can't really remember at the moment, and I don't want to say foolishness.
I mean, this foolishness really exists. Hmm. Alright, ice tables are proven to be an issue at all in all the animals. Alright, so using verbal X to generate expressions for the equilibrium constants here. Alright, so all we're doing, we're not given a specific k value. So how are we going to do this?
Sir, so according to how I do it, right? You got to write the KB expression.
The ka or kb?
KB, since it's this association to this one.
Kb. So this is dissociation. Well, this is an acid though.
Pardon?
This is an acid though. No, you said KB. That's what I'm
Uh,
wondering. Go ahead.
KD, like dog.
Okay, D. Oh, KD as a dissociation equation. Wait, what's KD?
The disassociation constant.
Okay. So in chemistry, we have something called KD, which is a partition coefficient, and that's like unique to chemistry. So I understand what you mean by KD as in K of dissociation. I understand that, right? But when we do that, though, we normally use Ka to represent that. Because, like, okay, the thing is now,
Okay.
Ka is the acid's KD. If you get what I'm saying. And KB is
Uh,
is a basis KD. So if we write this right, what you're saying is we're gonna have x over 0.30, which is equal to x squared over 0.30. All right, so where we go from here? We can't solve for anything.
sorry, not change.
Repeat.
Remember, I do anything different from your own. I don't have 0.3 minus x. I get minus 2x. Me equilibrium gonna be 0.3 minus 2x.
Mm-hmm.
So it's ethanoic acid. And the H is gonna be x. And for CH3COO minus is gonna be x.
Okay, what was gonna be x?
So did they give us like K8 or anything?
No, that's why I want you guys to try to have a go at this. It has to use x as variables to do this. No, go ahead. Somebody raising their hand. Let's see how long it takes to do this.
Sir,
Go ahead.
sir, sir, would we make X the subject?
And put the Ka in a random area. I mean, it's possible to make x a subject, right? But where are we gonna put the Ka? So okay, if you make x a subject, let's see what you do. You make x a subject, right? and that will now be the thing is, no, there's no value for, oh my, what's happening? There's no value for KA, right? So making x a subject, let's see whether or not that would change a thing. If we make x a subject, what would be the equation that we get from that?
Sir, 0.03 times Ka, and then to make x a subject, you would square root.
Make x a subject, you would square root both of them, right? But like, where's this taking us though?
Yes, sir.
It's not 0.03, 0.30. What I'm doing is trying to go through you guys' thought process to see what are we doing here. If we square root that now, right? Would that make a huge difference in anything that we're doing? Not necessarily. We're gonna get 0.54 times the square root of the Ka. So like, no, that's not what we're really doing here, right? We're not. They're not asking for anything too huge, you know, guys. They're literally not asking for anything too huge. So like, what they're asking for really is just to fill out this and let the equilibrium remain as x, right? It's not going to be this here, it's just going to be minus x here, right? Because that entire thing is going to be reserved far down here. And I think that would be the end of our issues, because this is, they're asking us to complete the table and do nothing else. And I think that is how you would complete the table. I don't see any.
Wow, sir.
Sir, but how you only getting 1x if you're getting 2 products?
Okay, so we're getting 1x if we're getting 2 products, right? It's because from the product
Supposed to
from
be
one product, right? The one product would produce 2 products. It's not that we get, okay, let me see. What we're doing is splitting our acid. Right? Let me just have a look at that. What am I trying to say? Okay, in equilibrium, let me not even use that either. How would I put this? There's something I used to explain this, but I can't remember it. Alright, so what's generally happening here is that we're gonna have a dissociation between the, let's show it up here, right? We're gonna have a dissociation between the acid itself, right, and the carbonate over here, right? If the acid itself will dissociate to give us these ions here, right, then the amount of acid that we dissociate, which would generally be X, right, will produce the 2 products, right? So this acid, right, let's call this acid X, right? This X will produce the overall concentration of this and the overall concentration of this. So it's not that it's 2x, you know. It's that from the original acid concentration, we get both of these concentrations, right? So it's not that you have to minus 2x to get these 2 over here. It's that from this x, you get this x and this x, right? So remember, x are just variables.
okay.
You know, it's not. Yeah, x are just variables. They're not the actual value, right? It's just showing what the increase would be, right? So it's not okay. Let me show what's happening, right? In equilibrium, right? Because the products are 0, we're going to have to take some of our reactants to create our products, right? Right?
Yeah, I'm
So
here with
we
you.
show that decrease by just it decreased by whatever amount of value, we don't know. It decreased by that value, right? But at the when we look at the products now, the products must increase by some arbitrary value. We call that arbitrary value plus x. We don't know why it's increasing by now. We don't know, right? But it's plus x. So it's increasing by some value. It's not that it's relational to the minus x. It's just that it's increasing by some value. And then at the end of the equilibrium now, right, the products themselves must have the same concentration, because that is one of the things that we use to define a dynamic equilibrium. So both of the concentration products must be x, right? While the equilibrium concentration for the acid will just be the what was minus up here, which is just our concentration minus the x that we have there. Is there a question?
Yes, sir. Sir. So, question, sir. So, if there was 2 moles of ethanoate, would we put plus 2x?
No. Because we're saying if there's 2 moles of ethanoate, what? Hold on, 2 moles. In what way? This is concentration, so when it's 2 moles, I get confused. What are you talking about? You talking about 2 mole per DNQ?
No, sir. I'm speaking about 2 in front of the ethanoate ion.
Oh yeah, hold on. So let's looking at this equation. If we had a 2 here, that you talking about?
Yes, sir.
In that case, we'd have to balance the entire equation and put a 2 here and put a 2 here. In that case, we have to balance the equation. So it's going to reduce itself back down to this. If that
No,
makes
sir. I'm saying, sir.
sense.
Well, not with the ethanoate, no, sir, but like with a different compound.
Oh yeah,
Say that you have.
Mhm. Okay, let's say that we have a dissociation of water, right? Let's say that we have. Okay, we're gonna look at something like this, right? Let's say that we have the dissociation of water into literally an oxygen atom, really, and 2 hydrogen atoms. Then this will increase by 2x. You get it?
Okay, sir.
Alright, so yeah, you increase by 2x. When we do the rest of the equilibrium questions, like on Monday, then they will come into comparison, because there's a hydrogen iodide question that, oh my word, that 2021 paper, that paper didn't fit. But alright, that paper there is not for the week. Alright, so let's have a look at this. Wait, is there anything on this page? Yeah, we just did that. Alright, so let's have a look at what's happening on this page. Okay, so generate the expression Ka for the reaction. What? The equilibrium expression obtained up there, right? So basically what we're going to be doing is writing the Ka expression. So the Ka expression for what we looked at up there would just be our CH3 COO minus, right, and our H plus, right, divided by the concentration of our CH3 CHOO. No. Okay, I think you guys can clearly see that I'm getting tired, because what was that? Alright, so COOH. There. That's our Ka, and that's the 1 mark. Lovely. So let's move on now. Calculate now the pH of this
Wait,
entire
sir.
thing.
Sir, if they say using the equilibrium expressions obtained, why are we using that?
The equipment. Oh my
I'm
gosh.
confused.
Oh, wait, hold on. Alright, so we're looking at that, right? Yeah, I didn't focus on using the equilibrium expression obtained. Alright, so what we're looking at, this is the Ka, right? So if you use the equilibrium expressions obtained from up here, these expressions here, right? We're gonna be using the equilibrium concentrations, right? So what we're going to be doing is plugging in these expressions, right? And then that would be what we'd use to get the answer. Would that make sense? So in the case of the equilibrium, right, we're gonna have, well, basically x squared up here, two x's. I'm gonna have this down here. So let's see. We're gonna have two x's here, so I'm gonna have an x here and an x here, and we're gonna have 0. I mean, the concentration is just going to be the original it's gonna be basically the original concentration minus the x, right? So it's gonna be the concentration of, let me actually erase that first. So how I would write this is CH3, right? Just writing back our CH3, COOH, right? And I would minus x from it over here, right? So it doesn't even have to be the concentration of x times x. So generally it would just be reduced to x squared over here. Alright, so I think that would make sense. So if you use the expressions obtained up there with the x's in the table, then this is what this expression would look like. Why I keep this and not put the 0. Whatever is because this is literally the same thing as the 0.30 moles. Same thing. Well, molar. That would be the same thing. Alright. So that up there. Let's say that now we have to calculate the pH of this molar solution at 25 degrees Celsius if x is that, right? So what we're looking at now is that the Ka itself is now going to be 0.0023 squared divided by 0.30, right? And this would be minus, right, the 0.0023. So we can get the Ka from that, but do we need the Ka in order to find the pH here?
No.
No, sir.
You
No.
just need
That's
to
kinda
put in, so you just need to use the regular pH formula and plug in the value for x.
Alright,
Right?
lovely. Let's
Isn't
see.
that what you're supposed to do? Yes.
3 marks. Plug in to get 3 marks. Alright, let's see. Because we can derive pH from Ka. But okay, so if we're just gonna do the pH thing, right? So what you're saying is that, go ahead.
Sorry for the question above. Did we have to write it in terms of x, or we could just leave it in terms of the ions and atoms?
They said using the equivalent expressions from above, and above we use x, so I think that's why it'd be good to use the x. But it says using the equivalent expressions from above, and the expressions that we got were x expressions. Alright. So leaving the Ka, people are suggesting that pH would be used as a negative log of the hydrogen ion concentration, and I think what you guys are suggesting is that we negative log 0.0023. That's what you guys want to do?
Yes, sir.
Everybody agrees with this approach? Yes.
Yes, sir.
What's the pH?
Yeah.
The 2.638. And what are the units?
It has no units.
Lovely.
It has no units.
No units. Alright. So this
Sir,
values,
I don't know why this question seems so complicated. Because this is the second time I'm seeing this question, and every time I see it, it's like my mind just tells me to work out something, and then I don't know.
The mind tells you use the Ka, right, to find the
Yes.
pH. Probably. All right.
So, okay, so can you show us how to find the pH using the Ka,
What an
just in
interesting,
case?
what an interesting proposition. All right. So how do you find the pH using Ka? Does anybody know? Is it even possible?
So you're gonna may write out your KA thingy. If the people give you KA, you're gonna transpose the formula in terms of hydrogen and you make hydrogen the subject. And then you're going to find the hydrogen and then plug it into your pH formula.
All right. So the thing is now we could use the Henderson-Hasselbalch equation. Wait, question. Could we use Henderson-Hasselbalch equation?
Huh?
Could we use the Henderson-Hasselbalch equation?
Oh, the one that says pKa plus log salt over acid.
Yeah, that one. I don't think we could use iron. I'm trying to figure out what we did here to see if this is the right thing we did here. But that is the concentration that we did this year. If we try to find it, calculate the pH of weak acids, right? We generally use the Ka expression. hmm Is this the right thing? Do you think this is the right thing to do? Couldn't we square this value and use the squared value, right? In order to find it. Let me see something first. Okay, but we have a value there. Alright, so let's have a look at this. Is this right? Give me a second, let me figure out something. 0.0023. I'm gonna square that value. I'm gonna get that. Give me one moment, please. What would that be? 0.030. But that won't work. Okay, that won't work unless we are given K. Alright, never mind. Alright, so how can we use Ka to find it, right? If we're given the Ka, right, but we do not know the hydrogen ion concentration, we can use that to find hydrogen ion concentration. We have the Ka and the concentration of the acid. So we can use it to find that, right? But using the Ka to find this now, I don't see why we would or how we would. What will happen here is that you'll calculate the K. Okay, there's a way of doing it now, right? Let me just say that first. You can use it and transpose it into the equation. But the only way I can think of doing that is using the Henderson-Hasselbalch equation, and that tends to be only for the buffers. We tend to use that for buffers.
So we don't need the K. So we don't need to know this method then.
Not necessarily, unless you're working with the what would say no,
Buffers.
yeah, the
Honest.
buffers, right? There's a but there's a different way to work it though. I don't know if I need to show you guys all the different ways they can work it. There's this way. It's a weird way, but there's this way where the pH is going to be equal to the negative log, right, of the square root of the acid concentration times the Ka. That's a way you could do it. And you can actually do this like rather simply if you have the K. You can do this rather simply if you have the K.
Say, you know what? We'll just stick to the simple way. Yes. As long as it gets us to 3 marks, we shall stick with the simple way.
Alright. That's interesting. Alright, so is this a question? Alright, so this is a simple question here, the voltaic cell. Alright, looking at the voltaic cell now, we have all of these things. So we need to label it, right? Is that what we're doing? Labeling. What is A? Why is A
is
such a curious question?
Flow of electrons,
A is,
Wait,
the,
what?
A is the flow of electrons,
or
right?
the direction of the electrons. Yeah, anyone.
So the flow of electrons.
Of the electrons. Right, what is B?
The anode.
The anode.
And C?
And
Anode,
C is
yeah.
the cathode.
The writing on the screen is terrible. So remember anode before the cathode. Oh, it's like that. Alright. Describe an observation expected during electrolysis. Liatin. An observation expected during electrolysis. What can you expect during electrolysis reaction? Go
You
ahead.
could expect the mass of the anode to decrease and the mass of the cathode to increase. That's one.
Yes. The mass of the anode is going to increase, and the cath is going to decrease, and we would know. Wait, the anode will decrease, right?
Wait, decrease.
Yeah, because I was thinking about that a while ago. The anode will decrease while the cathode will increase. The anode will decrease while the cathode will increase. We could. It depends. Well, color. If somebody was supposed to say color, it depends on the ions. Like, it doesn't have to be a colorful thing, right? I remember when answering one of these questions, somebody shouted at me.
Sir, on
What?
one side,
On one side, what?
on one side, would you also have like deposits forming?
Oh, so that's an example of like the mass increasing on the cathode, right? So depositing will happen, like electron
Oh,
plating,
okay.
like that will happen. I remember one session where somebody shouted at me that, oh, you're going to see the voltmeter turn on or a value on the voltmeter, and that is an observation. I'm like, okay, does that count? I don't think that counts. I don't think the voltmeter showing a
I
value
don't
counts.
think that.
Kaifan?
Sir, isn't that pretty like obvious? Right?
Yeah, it should be obvious.
Isn't that? Yeah. So
The thing is, if
that
somebody
wouldn't
wrote
really
that,
be an direct observation.
if somebody wrote that on the paper though, I would only give that mark, right? If I had to score the paper to make the person pass. So like, no, I wouldn't give that mark.
Sir, I
But
don't think Cape will do that. I don't think Cape will do that.
oh well.
I think if it wrong, just wrong.
Sorrows and tears. Alright, describe an observed change rather, if the cell components are based on the cell type here. Or it'd be an observation.
Sir, you would have deposits forming on the anode side, on the copper side.
You sure? Which one is the
Do
more
I need to state a
electronegative?
color?
I would love for you to do that. But right, which one is more reactive?
Sir, I'm not sure what you're trying to say.
Because the more reactive one, the
Oh,
higher one
the more reactive one would displace another one, so zinc would be more reactive.
Yeah, zinc is more reactive than copper.
No, copper is more reactive.
Ooh, that contention. All right, so which one is which? So in the electrochemical series now, right? What will happen for the electrochemical series? As you go up the series, the more negative it becomes. No? So zinc has a more negative cell potential than that of copper. Right? Copper is more positive than zinc, which is more negative. So what does that tell us?
It loses electrons more readily.
Which oozes? The zinc, right? Which one loses electron more readily, zinc or copper? Okay, let me write it down because in your booklet you should be able to get this information. So for zinc, we have negative 0.76 volts, and for the copper, we're gonna have something like a positive 0.34 volts. So, which one is the anode? Which one is the cathode?
Copper is the cathode and zinc is the anode.
And we could also see that based on cell notation, anode, then the bridge, then the cathode. Lovely, right? So what's gonna happen is that the zinc is gonna producing electrons, right? And then copper ions are gonna deposit onto the cathode, as somebody earlier said, right? And that would mean that we're gonna have a decolorization, right? Decolorizing of the solution. So the solution turns from blue to colorless. And we'll also see, the copper deposits. Right? So that should be fine there. State the chemical compound which is in the salt bridge. State a chemical compound which is in the salt bridge. What could be one?
Potassium nitrate,
Lovely.
sodium chloride. You can also have sodium chloride.
Alright.
And could you also have potassium chloride, or am I wrong?
You could technically have potassium chloride. But potassium nitrate would
Oh.
I would go for potassium nitrate. Like if there is ever a
Wait,
question, I'll
sure.
always
Yes, sir. I know. I know that.
Wait.
I know, sir. I'm just stating the others that you could have, but I know that potassium nitrate is the most common one.
Okay. Alright. Go ahead.
Sir, what was the answer for the last question?
We're gonna have a color change. We're gonna have blue to colorless, or we could say that the copper deposits onto its cathode. So we're gonna have copper deposits being formed on the cathode. And we get all that information from that little line of cell notation there. All of that information is from that. Alright, go ahead. Somebody reset that.
Sir, what color is the copper deposit?
Copper color, I guess? Like this reddish copper? That would be the copper color.
Oh, red. I'm just checking if it's Oh no, that would be copper oxide. Never mind. Okay.
If it would be black.
Wait, so basically you will have red copper deposits on the cathode, and that solution would turn from blue to colorless at the same time, right?
Yeah. Okay.
Okay.
Why I said red is because you know that copper is a reddish color, right?
Yes, sir.
Okay. Cause I didn't want it to seem like, oh, when it deposit it just becomes a bright red. No, it's just gonna be the same copper color. Alright? So that is that. And yeah, so the salt bridge can consist of any one of these things here, but we're just potassium nitrate is just it is the one that we strive to be. Right? It's the one that like the salt bridge strives to be filled with. You know? Copper nitrate is there. Not copper nitrate. Potassium nitrate, right? And we tend to use nitrates or chlorides because of their high solubility. And I think that's the end of module. Is that the end of module 2? Okay, so that's the end of module 2.